So, what we will discuss today is a continuation of what we were doing last time. So, we had learned about density matrix and how do we define density matrix, what happens when we have a pure state and when we have a mixed state, and how does the density matrix or the properties of the density matrix change in these two cases. And then we saw that how we can extend our knowledge of solving partition function and the corresponding or you can say the expectation values or of different thermodynamic parameters, and how can we extend our knowledge of our classical statistical mechanics to this density matrix formulation. So we will continue with that, and we will try to see how we can solve for the density matrix under different conditions and how it changes depending on the basis. And then we will see how the density matrix looks like for a free particle, or how does it look like for a harmonic oscillator, and from there how can we evaluate the average energy or the expectation values of different other parameters or variables. Okay, so this is how the session will go. We'll discuss some of the basic concepts, and then we'll discuss some basic problems, and I'll share the solution and we will discuss. And if you have any doubt, you can get back to me. Okay. So first, I'll do a recap of what we were discussing last time because it's important to remember those things in order to proceed forward. Okay, so what do you mean by a pure state is that when you can define your quantum mechanical system by one particular microstate, then it's a pure state. But then if your system is such that it can be in different microstates with different probabilities, then it becomes a mixed state. And you can see that this is the general expression for the density operator. But then if it is a pure state, then what happens is we just have one microstate defining the system. So for pure states, it's the outer product of psi, where psi with psi, where psi is the wave vector defining the microstate. And if you have a mixed state, in that case, in general, this is how your density matrix will look like. Okay, where rho k prime k is the probability that the system will spontaneously make a transition from phi k to some another state phi k prime. Okay, and if there is no such probability, then only the diagonal terms remain, and then we can have an expression like this. So this is how the density matrix changes depending on whether it's a pure state or a mixed state. And we had also seen that the properties of density matrix for a pure state and for a mixed state are slightly different. And then there are some common properties as well. So you can see for a pure state that we saw that rho square, where rho is the density operator, so rho square is equal to rho, and then trace of rho is always 1. And you'll see that means for a pure state, trace of rho square is always equal to 1. And then you can find the expectation value of any operator A by doing a stress of rho A. Okay. And then if you have a mixed state, what happens there is that here rho square is no longer equal to rho. And that means for a mixed state, trace of rho square won't be equal to 1. Okay, and then if you have to find the expectation value of any operator, then so this term here is the expectation value of the operator with respect to each microstate, and then you have to multiply with the probability of being in that microstate, and a summation over that will give you the expectation value. And that is also equal to the stress of rho A, where rho is the mixed state density operator. Okay, so now with that knowledge, we had also seen that how the density matrix looks like for different ensembles. Okay, so for a microcanonical ensemble, we know that it's a constant. It's constant for all the microstates. So there it would just be 1 by omega, where omega is the number of microstates possible. And then if you have a canonical ensemble, there what happens is this is the classical way of writing the density, the phase space density. And then if you have to change it to the density matrix formulation, we will get something like e to the power minus beta h, where h is now the Hamiltonian operator and it's divided by the stress of e to trace of e to the power minus beta h. Okay, so whenever we do a trace, we actually do a summation of over all the uh, eigenvectors or the basis vectors of the representation we are following. So if we want to write, or if we have defined our matrix in terms of some basis where the basis vectors are phi given by phi n, then we do a summation over all these terms, and that would provide us with the trace. And we saw that is equal to the partition function. Okay, and then if this is how you find the expectation value of some observable f. So if it is energy, you would get something like this, and that is also equal to minus del del beta of ln z, similar to what we had before. And then you can find the entropy from this relation, which is, so all the relations that we had done for the classical case fits in here. But the only difference now is that we are writing it in terms of matrices. Okay, so you're taking into account the so that makes it easier when we are dealing with quantum systems. And then for grand canonical, we have to have this extra term of mu n by kbt, which comes because of the fact that now we can exchange particles. Okay. So with this knowledge, this is what we had discussed in the last class. Now you would go forward and you see we try to solve for the partition function, try to solve for the density matrix and see how it changes depending on different states or the different basis vectors that we use. Okay. So the first question, this is the given density operator. Okay. So this is given as rho. Now we need to construct the density matrix. So how do we do that? So here, if you remember, so you can write a density matrix in different, like in terms of, or uh, in in terms of different basis vectors. Okay, so consider that here this plus z and minus z are the basis vectors. So now what do we do? Here we can see that it's written as the outer product of plus z vectors and then minus z vectors. Okay, so we want to construct the density matrix. What do we do is that this is the basic definition. Each density matrix elements can be obtained by this inner product, right? So first we operate rho on some basis vector phi n, and then we do a inner product with phi m, some other basis vector, okay? And then this value will give you the mn matrix element. Okay, so where m is the row and n is the column. So that means now when we have chosen the basis to be plus z and minus z, so this is how we are choosing our basis vectors. So what we have to do is that given this row, we have to find the individual density matrix elements. Okay, so that means now if we consider for the first case that phi 1 is equal to plus z, phi 2 equal to minus z. That means if we have to find row 1, 1, what do we do? So we have to do an inner product of this, like we have to find this term, right? So if we do that, we have to expand this, and once we expand, you would get something like this, right? Uh, Kamalesh?
Ma'am?
Yeah. Yes. So, are you following? Like when, so should I explain, or did you follow whatever I said till now? This question.
Yes, ma'am, I follow.
Yeah. Okay. So that means for each of the matrix elements, what you have to do is you have to find this term. So for the first term, you do row 1, 1. So here 1 means plus z basis vector. So this is how you would get the first element of the density matrix. Okay, so what would be the second element, like what would be row 1, 2, which is the element of the first row, second column. So that is row 1, 2. How do you find row 1, 2? How will this term change there in that case? Can you tell me?
Ma'am, the last one is minus, is it?
Huh?
Then
Yes, I didn't get you. What did you say?
Ma'am, the last one is minus, is it? The
Hmm. Okay.
the outer
So in
product.
this case, in this case, you're saying that this term would be minus z, is it?
Yes, ma'am.
Okay. So see, one in this case it won't matter, but generally it's like this is the first. So you have to go along a row and a column. So in this case it would be something like this, right? This is what you're saying.
Yes, ma'am.
Yeah, right. So what would it come out to be? If you solve it, what will you get?
Okay, ma'am. Ma'am, can you to the
Yeah.
previous slide?
Okay. Yes. So you
And
have to write. So this is your row, right? And then first you operate row on minus z, like for your next question. So this is the form, right? So operate row on minus z, see what you get, and then take the inner product with this term, right? With plus z.
yes, ma'am. Ma'am, is it 1/4?
Is it 1 by 4? Try solving. Do you get 1 by 4?
No, ma'am, it is 0.
It's 0, right? Because plus z and minus z are orthonormal. So inner product of plus z with minus z will always be 0, right?
Yes,
So, so you get 0. So similarly, what will happen to row 2, 1? That will also be 0, right? So row 2, 1 will be something like this. And then that also comes out to be 0, correct? And then what happens to row 2, 2? What do you get in that case?
I'm 1/4.
4. Right. So you, if you just look at this expression, in a way this also tells you, right? Because rho is already expressed in terms of this basis vector. The expression of rho that you get here is already based on this basis vectors. And then if you expand, you would get the same thing, right? So that means this is the first term and that is the, so you just have the diagonal elements, correct? So that means if you just find the individual density matrix elements, and then if you put it together, you would get something like this. So depending on the basis that we have chosen, this is the density matrix that we get. Okay. So this was the first question. The first question was that we have to find the density matrix. Now, is it a mixed state or is it a pure state? How do you define that? What do you think? Is it a pure state or a mixed state?
A mixed state.
It's a mixed state. Okay. So so why do you think it's a mixed state?
For mixed state, the probability values multiply along the diagonal elements. So,
No, see, probability values multiplied along the diagonal elements will always be so in whatever basis you do. So you understand, like in whenever we are diagonalizing, the each coefficients will actually tell you the probability. That is always true. But then, what is the physical significance of writing the density operator in this way? What does this tell you? Like if I say, what does this thing mean physically? What will you say? It's a mixed state. That's correct.
ma'am, sum of all the diagonal elements is 1 because the probability is conserved.
Correct. Okay. But then, so if suppose if I had half and half, that would be a different state, right? Half of plus z and half of outer product of minus z. If I had that, uh, that would be a different state. This is a different state. So if you have to physically explain this state, what would you say? So this state, in a way, tells you, so like if you look at this, this will tell you that it has 3/4 probability of being in plus z and 1/4 probability of being in minus z. That means the system can be in two microstates, plus z or minus z. It is not defined by one particular microstate, right? So that is why it's a mixed state. Correct. That's the physical significance. That's how you have to define if you or you have to explain if you have to explain physically. It's clear, right? So this you have to, if I say what does it mean physically, you should tell that this means that the state has 3/4 probability of being in plus state and 1/4 probability of being in minus z state. That means there are two possible microstates that the system can be in with the corresponding probabilities, and so it's a mixed state. Okay, that is the physical description, right? And then now there is a mathematical way of also proving that it's a mixed state. How do you do that? So because see, this is very trivial. Even looking at it, we can tell, but in some cases it won't be this trivial. So there is a mathematical way of proving or confirming that it's a mixed state. How do you do that? So there you have to remember that for mixed state, the trace of rho square is not equal to 1. While if you have a pure state, then rho square is equal to rho, and then trace of rho square is equal to 1, right? So in a way, trace of rho square gives you a measure of the purity of the state, right? So if it is equal to 1, then it's a pure state. If it is less than 1, that is if it is not equal to 1, then it's a mixed state, right? So can you try to solve the trace of rho square for the given uh, mat like given density matrix? This is your given density matrix. So what will be your trace of rho square?
Yes, ma'am. I will try.
Yeah.
Ma'am, it
So
is by
yeah.
16.
Yes.
Ma'am, is it 10 by 16?
Yeah. This is what you get, right?
Yes, sir.
So there's a easier way of like you don't have to do this entire calculation. What you can just think of is that see, it's already in diagonal form, right? So if there is a square matrix, and so if you have the eigenvalues of some matrix A, then the eigenvalues of A square, the A square matrix will be given as lambda square, right? And trace is nothing but the sum of the eigenvalues. So in a way, you can just, so because this is already giving you the eigenvalues of rho. So what would be the eigenvalues of rho square? It would be square of this and square of this. Okay. So you can just look at it and say that it's 9 square by 16 plus 1 by 16. So it's 10 by 16, right? So this properties of matrices can help you solve these questions much faster. You can always go through the entire process, but at times it can be even easier to just look at it and use the properties. Okay. So that means the trace of rho square is less than 1 here, and that proves that it's a mixed state. Okay. Now then the next question was that, 1 second. Huh? Yeah. Okay. So now the next question that we wanted to have was that how do we find the expectation value of the different spin, like sigma, I think Sx, Sy, and Sz, right? What was the question? Let us go back. So the question was, we have to find the, so what is the average spin along X, along Y, or along Z for this state? So how do we do that? So for any operator, if we have to find the expectation value, we do a trace of rho into that operator, right? That's the way how we have seen we have to find the expectation value. So now what we know, we already know rho in some basis, depending on like with respect to some basis, we know what is rho. We have to write Sx, Sy, or Sz in that basis, right? And then if we multiply both of them together, we would get rho A, or like rho Sx, rho Sy, rho Sz. And then we have to take the stress of that thing. That would give you the expectation value. So here, so we have to find the average spin. So for that, we have to know the spin matrices. So there comes the Pauli matrices. So sigma x, sigma y, and sigma z. For a spin half particle, this is how the spin matrices goes. Okay. So here, the expression that, so that means you have to write this matrices in terms of your plus z and minus z vectors, right? So if you look at sigma z at first, how will you write this as? So looking at this, how will you write uh, in terms of the basis vectors? How do you define that? So you define it something like this. So your h cut is just to, so sigma does not have h cut, but in the definition of as like S or the spin matrices, you can include h cut. Okay, so that is to have this dimension maintained. So now if you look at Sz, so that is h cut by 2 into, so like outer product of plus z and plus z, and then you have minus 1, so that gives you minus h cut by 2 outer product of minus z, right? So any matrix can actually be written in a form like this. Okay, so whenever you have some matrix and you know some basis vectors, you can write the matrix in terms of the basis vectors in this way. So here what we have done is we have written all this spin matrices in terms of the plus z and minus z basis vectors. Correct? Is this clear till here?
Yes, ma'am.
Yeah. So now we know Sx, Sy, Sz, we know rho. So what we have to do is we have to multiply, suppose we have to find the expectation value of Sx, okay, or Sz at first. So what do? We find the trace of Sz rho. So can you try solving that and see what you get? So you have to multiply Sz with rho and then take the trace of it.
Ma'am, I have doubt.
Yes, tell me.
Ma'am, can we directly multiply the uh, two matrices? Is that on the row directly, or we do the
Yes, you can. So you can do both. What you can do is you can write, you can use, suppose if you are using Z, so you can use this expression and then you can use the outer product representation of rho and do the multiplication, or otherwise you can just multiply the matrices. That is, both will work.
okay, ma'am.
Yes, because both means the same. It's just representation. So whatever is comfortable, like whatever you are comfortable with.
Okay, ma'am. Thank
Yeah. So your SZ will be h cut by 2, 0, 0 minus h cut by 2. That is your sz. Okay. And then you know rho. Rho is given by 3 by 4, 0, 0, 1 by 4, right?
Ma'am, I get h cut by 2, 3 by 4, 0, 0, minus 1 by 4.
1 second. How many values did you tell?
Ma'am, h cut by 2 outside,
Okay.
then 3 by 4,
Okay.
0,
Hmm.
0, minus 1 by 4.
Okay. So what would be the trace? Trace is the sum of the diagonal elements, right?
H cross by 4.
Right. So this is same as what they have done, right? They directly multiplied the matrices, and they have done it. I think you did by multiplying the matrices, and they have written it in terms of this outer products and so both are exactly fine. So this is your expectation value of sz. So similarly, you can find the expectation value of sx or sy, right?
Yes, ma'am.
Right. So try solving. It would be something like this, right? Sx and sy. So this is Sx. So now you're multiplying with h cut 0 h cut by 2 minus h cut by 2 0.
Okay.
Like you remember, you need to remember this polymatrices. Okay, this is very fundamental. So now in this case, this is how S sigma S is. So Sx will be h cut by 2 into this, right? And multiply with the density matrix, and that will give you, and from there find the trace.
Okay.
So it's just matrix multiplications. So maybe I'll share the solution. So it would be it's 0,
0.
right? Yeah, right.
Yes.
So similarly, if you find sy, that will also come out to be 0. Okay. But then one thing is that, see, in this question, you might not even have to, so you could have just said that sx and sy would be 0. How? If you would have thought it physically, right? Because physically, when you look at the density matrix, you are seeing that it's defined in the plus z minus z basis, and then it tells you that it has 3 by 4 probability of being in plus z and 1 by 4 probability of being in minus z, right? That is plus like up spin along z or minus spin along z, right? So there is no spin orientation along x or y, right, physically. So that means you can just look, so in for this question you could have just said that physically if I think sx and sy would be 0, right? So that means when your, so if your so try to think whatever whenever you are getting a density matrix, try to think what it means physically that can make your uh, like problem solving much easier. Okay.
Okay.
Okay. So now this is a state of a system. This is something which we had discussed in the last class, right? So suppose if your system is defined uh, by this wave function, okay? So what would be the density matrix in the up or down spin? So this is something which we had done in the last class. Can you tell me what it will be? So what is the what is the general way of finding the density matrix elements? You know that you have to do that inner product, right? Phi m rho phi n, right?
Is it of uh, of 0 0 of?
Is it?
I
So try
remember.
to no, don't try to remember. Okay, try to find from this expression. So this is your state, right? So you are saying that the system is defined by this state, correct? So that means there's only one microstate. So this is the pure state, right? Because your system is specified by one microstate, correct?
Yes,
So
ma'am.
then what would be the density matrix? Density matrix is given as outer product of psi, right? That's the basic definition of density matrix when we had done it for a pure state, correct?
Yes, ma'am.
So you have to find something like this. Do you remember now? So if your state of the system is already specified, like your system can be in only one particular microstate, that means it's the pure state, and in that case, you can just do this outer product, and that would give you the density matrix, right?
Yes, ma'am. I get it.
Right. So now, if this is your density matrix, so whenever you are doing it, you are actually doing it in this up and down spin basis, right? Because you can say that when you are defining the state, you are defining it in terms of this basis vectors. So you are in this basis, up and down spin basis, right? So this is the sigma z basis. This is how we are defining it. Now suppose that you want to go to some another basis, okay, where the basis vectors are given by this and this, right? So this was your initial basis vector. Now you have this basis vector. This is your basis vector. This is one basis vector. This is another basis vector. So how will you find the density matrix in this basis representation? What would be the way? What do you think? Like what should be the way? So
By
basically, tell me. Tell.
by multiplying with the ortho orthogonal matrix, that will bring to another basis.
Uh, Okay, so so when so any matrix, if you have some matrix and you have some matrix elements, that is with respect to some basis. Now, when you go to some another basis, how will you find the individual density, like individual matrix elements in that basis? What do you do for that? So what you have to do is see here. This elements, this basis vectors are written as superpositions or linear superpositions of the initial basis vectors, right? So that means you can write your new basis vectors in terms of the old basis vectors. You can do that. That's how this is being done. And you know the density matrix in the old basis, correct? Clear, right? So you know the density matrix. This is your density matrix in plus z minus z basis vectors. And then your new basis vectors, which we are defining it as up x and up down. These two basis vectors are written as superpositions of the old basis vectors. So if you write it in terms of column matrix, you write it something like this, correct? Is this clear? Here you are writing the new basis in terms of the old basis vectors. Is this clear?
Yes, ma'am.
Right. So now what the question asks is that you have to find the density elements considering this one and like up x and down x as your basis vectors. So that means what you have to do is for the first element you have to do something like this, correct? So in whatever basis you want to find your density matrix representation, you have to do the inner product with respect to the basis vectors of that basis, correct? But
Yes,
because rho now is given in like what you have with you is the rho which was given with respect to the old basis vectors, you write this new basis vectors in terms of the old basis vectors. Okay. And then you do this inner product, right? So try to solve this and see what you get. So operate rho on this, right? And then do an inner product with the ket of this, right? So you're doing something like this, right? So this is the first, like first row, first column element of the density matrix. In this, considering this as your basis vectors,
ma'am, I get one.
you get one, right? Okay. So what are the other basis vectors? So suppose what would be row 1, 2? You will have you will have down x, right? Here, like what will be row 1, 2? So before solving, think what it can be.
Can you give any physical uh, in
Yeah, a physical meaning will come out. So if you solve it, finally you will get a physical meaning out of it. But if you just now, maybe I'll give you a hint. So this is your sigma x, right? This is your sigma, like the sigma x up, and this is your like what am I saying? Spin up with respect to x and spin down with respect to x. right? These are your two basis vectors. And what was your initial state of the system? How was the state defined?
In terms of spin along Z direction.
Hmm? So this is your given, this specifies your state, right?
Yes,
So can you find some similarity or so what does this mean? You are writing this state with respect to these basis vectors.
yes, yes.
So maybe if I simplify, you are given, you are said that you have a spin up state. Okay. So that means your system is specific with respect to Z. Okay. Forget this question for now. You are said that you have a system where you are in spin up state, right? So your system would be specified by this up vector, right? If you are in this basis, suppose. So your system would be specified in by this wave function, the up state, correct? Now, what is the probability that it is in down state or some other state?
0.
Correct. So now, if you look at this basis vector, these are the two basis vectors in terms of which you are defining your density matrix. And your given state is this. So if you look at the basis vectors and if you look at the state, what does that mean? What does that mean physically? Are you understanding the question?
Yes, yes.
Okay. So you have two basis vectors and then you have your system defined by some wave function. Generally, it can be a superposition of the different basis vectors, right? In this case, what do you see? You see that your state matches with one basis vector. Is that correct?
Yes, ma'am. Ma'am, so all the other matrix elements, so
Okay, so if it is zero, what does that mean physically?
it is in uh, spin up along its direction,
Right. So that means it's
particular
yeah,
location.
it's only in this state, right? So that means the probability of this state or a transition from one state to another. So what does the cross terms mean? The cross terms mean that there can be a transition from one state to another. But then your system is specified to be only in this state. So when you are writing the matrix elements in terms of this basis vectors, what will happen is your system or the state matches with one particular basis vector. That means you're always in that only that density matrix element remains, right? Because rest all are zero, because rest all probabilities will be zero, correct?
Yes,
So that means here where you are getting row 1 1 as 0. And now if you want to find row 1 2, if you do it explicitly, you will see that it turns out to be 0, right? Half minus half, you'll get something. So it's half minus half. So this two terms become 0. So ultimately it's 0. Similarly, row 2 1 will also be 0. And if you do row 2 2, that would also turn out to be 0. Correct? So that means in this basis given by these two vectors, which are different from the basis in which we were doing it for the first case. So in this basis, your density matrix looks like this. So this, in a way, again tells you that it's a pure state, because now you only have one non-zero element, okay, and all other terms are zero. That means you have only one particular microstate in which your system lies. Okay. So what did we learn from this question is that the density matrix elements will depend on what basis we choose, right? Initially, we had the density matrix given as half, 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 half. This was the density matrix when we had chosen the sigma z basis, right? And then when we move to sigma x basis, which is given by this basis vectors, we get this representation of the density matrix. So depending on what basis we choose, our density matrix elements will differ. That's general for any matrix. Depending on what basis you choose, the matrix elements change. Okay. And then we learned that given a density matrix in some particular basis vector, how do we write it in terms of basis vector, in terms of some other representation, which is given by some new basis vectors. So we saw how we can move from one basis to another. Okay. And if we look at this particular density matrix in particular, because it has only one non-zero term, that means it's purely in this up state along x, and then it's a pure state. So if you do rho square, you'll see that that will be equal to rho, and that would again show that it's a pure state. Correct. Okay. So now if you do sigma x, what will you get? So sigma x meaning this is the expectation value of sigma x. So you're doing a stress of rho sigma x, right? So you know rho, you know Sx. If you multiply and do a trace of it, what do you get? But don't do this mistake of writing rho in some basis vector and Sx in some other basis vector. Okay, like with respect to some other basis, both should be in same basis when you are doing this kind of uh, like whatever you are doing, your representation or the basis representation should remain same. So you know the representation of rho in the sigma z basis, you know the representation of Sx in the sigma z basis, then try to multiply both of them and then find the trace of it. What do you get? So what is your rho in this case? Which basis are you choosing and what is your rho?
Ma'am, is it h cross by 2?
Okay. So you did something like this, right? And then it comes out to be h cross by 2. Good. So, and then now if you do the expectation value of Sz, what will you get? So then you have to multiply by 1001 in place of 0110, right? Now, while you are trying to solve this, think physically again. You just learned that your system is in spin up state with respect to x. So when you do the expectation value, what you get is actually h cut by 2, which is the spin up the spin for the up state, right? You get h cut by 2 when you do Sx. So that matches with our physical understanding, correct?
So for ASZ, it is 0, right?
For Sz, it should be 0. So do you understand that physically? Why Sz is 0?
Yes, ma'am.
Right. So similarly, what will be y? The expectation value of Sy?
It will be 0.
It will also be 0 because you have your system in one particular microstate, which is in up state with respect to x, right? So that means when you do an expectation value, only the spin state with respect to x has a non-zero expectation value. Others are all 0, right? So like these things will be like if you just solve it mathematically, you would get some answer. But at times, if you think physically, you don't even have to solve. Okay, right. So now in this question, you are set that your system is in 50-50 spin up and spin down state along Z. So first tell me how the density matrix of the system should look like. So what basis vectors will you choose?
Uh, no, no, no.
Hmm? Hello?
Can you hear me?
Yes, yes, yes.
1, 0 and 0 minus 1. Right? Still
1,
along.
0 and 0 minus 1, right? Spin up and spin down with respect to Z. So those are your spin up. And so you can write it as up, like up state and down state. So these are your two, like you can represent them in that way. And that are your two basis vectors, right? So now it's said that your system has half probability of being in spin up and half probability of being in spin down. So how do you write the density matrix? Think physically.
Ma'am, 1 by 2 of spin up plus 1 by 2 of spin down.
Yes, outer product, right? This is called outer product. So half of up and half of down, right? This is what you meant?
Yes, ma'am.
Yeah, right. So now, very good. So now if this is your row, how do you find Sx? What will be your Sx?
I'm multiplying with the Pauli matrix.
Yes. So you have to multiply row with the Pauli matrix, correct? And then take a stress of it.
Ma'am, is it zero?
Okay,
Trace is
right. So the trace is 0.
zero.
Okay. So if you do sigma y, that would also turn out to be 0, right?
Yes, ma'am.
So what the solution tells here is that this is your rho. If you write rho, this is what you get, and this is proportional to unit matrix. So that means when you are multiplying rho with any of the poly matrices, you are actually multiplying some uh, some constant into the unit matrix with the poly matrices, and the poly matrices are all traceless. So that means all these average values will turn out to be 0, right? But now let us think physically. What is this telling us? So your system is in has half probability of being in spin up, half probability of being in spin down along z, right? So that itself tells you that sigma x and sigma y should be 0, first of all, right? The average along x and average along y should be 0, because your system can only have spins along z. That is what your question says, right? So physically Sx average, Sy average is 0. Now what happens to Sz? It has half probability of being in spin up, half probability of being in spin down. So when it is in spin up, what is the corresponding Sz value? Or
Zero.
should be the, no, 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 no. Think that your system is in spin up state. So what is the corresponding spin value, Sz value? What is the Sz value corresponding to spin up state?
Ma'am, can you repeat?
So if in your Sup so now just think about Sz, okay? So Sz you can have two states. One is spin up, one is spin down, right? So what is your spin value or Sz value when it is spin up?
Ma'am, X cross by 2.
H cross by 2. Okay. And what happens when it's spin down?
Minus X cross by 2.
Right. And now you have 50-50 probability. That means what is the average? It should be half into H cross by 2 minus half into H cross by 2, correct? So you're multiplying the corresponding probabilities with the respective spin values. That's how we generally do averages, right? And what you get 0. So if you think physically, what happens? Your system is not along x, the spins are not along x, not along y, it's along z. And along z, it has 50-50 probability of up or down. That means if you now do a sum, if you do an average, it would, on average, it would turn out to be 0, because up spin and down spin both has equal probabilities, correct? So this is how you have to think if you have to think physically, right? Clear?
Yes.
Right. So now in this question, you have your density matrix. And here, in this case, the system has 50-50 mixed state, is defined as 50-50 mixed state with respect to x-axis. So how will you write your density matrix now? What will be your density matrix? So before finding the density matrix, you have to find the basis vectors. What
Ma'am, the
should be,
base
yeah, tell me.
root to 1, 1, and another one is 1 by root to 1 minus 1.
Right, because these are the basis vectors of sigma x, right?
Sigma.
Like, right. So if that is your basis vector, now what should be your density matrix? So you can write the two basis vectors, you can symbolically represent it as up with respect to x and down with respect to x. And then it said it has 50-50 probability of being in up x or down x. So how do you write the density matrix in that basis? It should be something like it has 50% of the spins in this state, 50% of the spin in this state. So how do you represent that? So in the last question, what did you have? You had 50% probability of being in up state with respect to x, z, and 50% probability of being in down state with respect to z. And then how did you write it? You wrote it in this form, right?
Yes, ma'am.
Right. And now what happens is you were said that it's quite similar to this question, but now the spins are along z, along x. So what should be the density matrix? How should the density matrix look like?
Do we take any product with uh, 1 1?
Mm, the one. I did not get you. So if
Do
you have
we
two basis vectors, you have in any basis, you have two basis vectors, and there is half probability of being in one basis vector and half probability of being in the other basis vector. How do you write the density of density matrix? Okay, see, so it should be something like this, right? Half of the outer product of the up states with respect to x and half of outer product of down states with respect to x. This is
yes,
exactly
ma'am.
similar to what we did in the last question. Just the difference is that there the basis what with respect to z now is with respect to x, right? So now if this is your density matrix, what if we have to write it in terms of the matrix form? What will you do? You have to break this, like you have to write the expressions completely. You know what is sigma, like what is up x and up down x, right? Expand that and see what you get. Anushka, did you understand the question?
Yes, ma'am.
Yeah, okay. Try solving. Find rho.
Ma'am, when we say with respect to x, does that mean it is polarized along x?
Yeah, you can say in that way that if you have collection of spins, out of that 50% will be along up and 50% will be along down. So in a way, this is not polarized, right? Because it has 50-50 probability. If it was completely along one direction, then you can say that it's polarized,
Okay, ma'am.
right?
Ma'am, is it of 0, 0 of?
Okay, so let's see what happens. You get something like this, right? And if you look at it, you'll see that this row exactly matches with the row that we had got in the last question, right? So even here, now if we have to find sigma x, sigma y, and sigma z, by the same logic, it would turn out to be 0, correct? Do you understand why it's 0?
Because the spin is along x direction.
So the spin is along x direction. That means sy and sz should have the expectation value to be 0. Fine. Now what happens along x?
Ma'am, it is
Why is
0
it
because
0? Yeah, tell me.
person probably being enough and
Right.
with the
So
same
again, the
probability.
same logic. Again, the same logic, right? So if you have like whatever is up and then the down, if they are equal, then they'll cancel each other. And on average, the spin is 0, right? So what does this tell you in a way is that the only difference between this question and the last question was that in that system, it was 50-50 up down along z. Here it's 50-50 up down along x. But then, in a way, that means we have no idea in which direction the spin will be. The x and z can be just dummy variables here, right? It can be spin up or spin down, and that so the, like physically x and z doesn't make any difference, right? So that's why the spins are actually completely random because it has 50-50 probability of being in up and down in along some direction. That means in a way we don't know what the spin is. Like we are in a state of total ignorance. Okay, so that means here just by choosing one particular axis won't change anything. So if you had if I would have said that you have 50-50 mixed state along y-axis, it would have given you same result, right? Or maybe along some particular another particular direction, any particular direction. It can be either up or down. So that all this means the same because in a way you can consider them as dummy directions, and then you don't have any idea what the state will preferably be in, right? So that's what physically these two questions giving the same answer mean. Now, another two-state quantum system can be analyzed in the same way, and that is the polarization state of beam of light. So I had seen in the assignment, I guess there was some question which says that it's polarized along some direction, and what would be the density matrix or something like that. So that means in that case, if you say that there could be two possible, so the beam is traveling along z, and then there are two possible polarizations, either along x or along y. That means in that case also you have two basis vectors, one which means polarization along x, one which means polarization along z. And then if you say that it's 50% probability of being in along x and 50% probability of being along y, that means in a way you are in a complete random mixed state. And then again you would get the same density matrix. But then if you say that you are particularly aligned, or if you are polarized, if it is a polarized light along x maybe, that means that particular density matrix element will be non-zero. All others would turn out to be 0. Is that clear? Then it's a pure state. Is this concept physically clear?
Yes, ma'am.
Yeah, Kamlesh, is it clear? Yes, I'll consider it's clear. Okay. So now,
Oh,
okay. So now what we saw, we tried to solve the density matrix and
ma'am.
we saw how, huh? Yes.
Yes,
Hello.
ma'am. It is clear.
Okay. So what we learned till now is that we learned how we can write density matrix under different basis representations. So that would give you an idea how to solve your first few questions of your assignment. I was looking through that. So there, if you have some system and then in some basis, and then you move to some another basis, so you have to do whatever we were doing till now. Okay, so you have to find the new basis vectors in terms of the old basis vectors. You have to write the new basis vectors in terms of the old basis vectors, and then you have to find the individual matrix elements as we were doing. So that would give you an idea how to solve. So that gave you an idea how to solve the all those kind of questions. Okay, finding the density matrix under different basis representations. And what do you mean and what happens to the expectation values depending on the density matrices. So what we will now do is we'll see how we can write the density matrix representation for a free particle in momentum representation. So when you have a free particle, that means your Hamiltonian is given as p square by 2m. So it's the Hamilton is a function of the momentum, right? So, and then we know the Hamiltonian operating on the energy eigenstates will give you the energy eigenvalues. So phi k are the energy eigenstates, and then what you get, this E is the energy eigenvalue. Now, because your Hamilton or the energy operator is actually a function of the momentum operator, that means you are in the, so they're commuting, right? H is commuting with P. That means they have the same set of eigenvalues or eigenvectors. Not same eigenvalues, but the same set of eigenvectors, right? So here, now in for a free particle, what happens is we know that it can be represented by a wave which goes as e to the power I k dot r, and 1 by root over v comes because of the normalization, and then this k goes as 2 pi by L nx ny and nz. So this comes from the boundary conditions. So this is how I think this is all this has been done in quantum mechanics, I guess, if you this is supposed to be done. But if you think physically also, you have free particles. So the free particle can be represented by a wave, but then it's within a volume. That means it has to satisfy the boundary conditions. So the wave function should go to 0 at the boundaries, and that would give you the possible values of the wave vector k, and then it's normalized by 1 over root over v. So this is how your state is represented with respect to or in the momentum space or momentum. This is the momentum representation of the wave function, right? So what you have to find is you have to find the canonical density matrix. So what you do, just like what we were doing in the last case, what you have to do is e to the power minus beta h. Obviously, later we'll see that. So rho is defined as e to the power minus beta h by z. But first we're evaluating this term. Okay, e to the power minus beta h, and then we take this inner product. So this gives you the corresponding matrix elements, right? And here what you see is when this operates on phi k, because it's a eigenstate, what we get? We get this corresponding value, right? We get the corresponding h square k square by 2m out of it. And then this inner product gives you a delta function because these are orthonormal vectors, okay, or orthonormal wave functions. So this is how the each matrix element looks like. And then obviously this is divided by the partition function. When you define rho, it's defined as e to the power minus beta h by z. So how do you find z? Z is obviously the trace of this term, e to the power minus beta h. So By trace, we mean a summation over all values of k. Okay, and then k now is a, so if you consider that your volume is quite large, where the energy levels are quite close to each other, what we can do is we can consider k to be a continuous variable, and there we can change it to an integration. So v by 2 pi whole cube comes because of the normalization. So this is the, uh, you can say, the volume in the k space taken by 1 microstate. And then if you do that, you would get something like this. So if you remember, this is same as what you had got from the canonical ensemble like calculation, what we did classically, right? So now if you put this expression for z in the final expression, what would be your expression of rho? It should be this term, okay, this term divided by z, right? And this is what is given here. So this is your density operator. So each element of the density operator, which is defined by these indices k prime and k, is given by this expression here. What this delta function tells you is that the density matrix is diagonal. Okay, that means you'll have only the diagonal elements and all other terms are 0. So you are, that means you are, so in the momentum distribution, you're already getting a diagonalized density operator. Okay, so that's because your Hamiltonian and your momentum operator actually commutes. You are in the same, you have the same eigen basis for both the operators. Okay, so now what happens is, if we now go to the position representation, you will see that just like the other questions which we were solving, depending on the basis vectors, the description or the matrix elements of the density operator change. So even there you'll see that if we now move to the position representation, our individual matrix elements of the density operator would change. So what will then happen is that now this is your you can say the density matrix elements for in the momentum representation. And then what you have to find is you have to find this that is in the coordinate representation. So you do this summation. Here you have used the completeness relation. So you are doing a summation over k prime and k, and then you have included this outer products because k prime and k, this whole set of basis vectors are actually complete. So summation over k prime, outer product of k prime, or the summation over k, outer product of k for all values of k or k prime will be 1. Okay, so you can include this expressions here. And then if you break it, you would get something like this. You change it to integration because of the same reason that in this case you can consider that the energy levels are quite close to each other. So you can consider k to be a continuous variable and you get something like this. Okay, what you have to then do is you have to write this in terms of a whole square so that you can use the Gaussian integral relations. And if you do that, okay, these are just like simplifications in order to get to a whole square representation. And there you would get something like this. Okay, so if you look at this expression, this is what you will get, right? So now if you have r prime equal to r, what will happen is you'll just get a constant value, right? And in this representation, you see that you don't have a delta function, rather you have this expression. So that means you have a non-zero non-diagonal term. So when you are writing in the position representation, you'll see that the density matrix elements do have non-zero non-diagonal terms, while in the momentum representation, we had only diagonal terms, right? So this is how the diagonal terms will look like. This is the diagonal term values, and this is the non-diagonal values, right? So what this tells you is that the non-diagonal elements can be interpreted as the transition probability of particle moving from some position r to some new position r prime, okay? And you can see that it's a non-zero value. Now what happens is if you go to larger temperature, what happens at larger temperature? Lambda, which is the thermal wavelength, goes to 0. So in that case, it's hardly observable. This transition from one state to another is hardly observable. And so what happens is there this term goes to 0. While for low temperatures, you can see that lambda can be very large And then what you will get is that you'll get this kind of non-diagonal terms. Okay, so in a way this tells you why we get back, why we get the classical relation like results back when we go to higher temperature, while at lower temperature the quantum effects become quite uh, significant, right? So this is how it looks like if you have a free particle in some volume V, and in different representation, the momentum representation and the position representation. Is this clear?
Yes, ma'am.
Yeah, okay. And then now if you go to an harmonic oscillator problem, what you will see here is that, so this is a, if you go through the class videos, you will get the entire solution. I haven't discussed the entire stepwise derivation here because it's very involved, but the concept goes as goes similarly. So this is how you are defining the different energy eigenfunctions. Okay, here these are the Hermite polynomials. So here what you have to do is when you say that you want to find the density matrix, you again have to do those inner products of in order to find the individual matrix elements. Okay, so if you want to do it in the energy representation, that is very easy to do. So in that case, what you will do is you'll find Z, and Z is the trace of e to the power minus beta h, and then you can do a summation over all the values of n, which signifies the different energy levels, and you get something like this, right? So this is your partition function. While in the position representation, the expression, so in the that means you'll get this diagonal terms there, right? But in the position representation, what will happen is now you have to do something like this, where you do an inner product for different uh, basis vectors in the position representation. So in that case, it's a very involved derivation. You can look like it would be available in any book, textbook, or even in the class videos. So I haven't done it here because it would take a lot of time. But then, so you'd get something like this. Okay, so you can see that it do have this non-zero, non-diagonal terms. Okay, and the diagonal elements of the matrix directly yield the average density distribution, and that looks something like this. Okay, so that in the high temperature limit, again what we see is we get back something like this, which is the classical, which matches with the classical phase space density, and if you do the other limit, you would get back the quantum limit. Okay, so now with all this knowledge, let us try to solve a simple question. So this is your simple harmonic oscillator. Okay, this is how you have defined the Hamiltonian, and then you want to find the partition function. So I have already discussed this thing in the last two slides, but can you tell me like what should be the partition function for a single harmonic oscillator? Can you try solving? Try to do it in the energy representation, right? And once you find the partition function, how can we find the average energy? So that's the first question. Can you try solving? So partition function meaning it would be summation over all values of n e to the power minus beta En, right? Where En are the different energy eigenvalues for different energy levels. I had just discussed it two slides back, but I was doing it very uh, qualitatively. Like I just said, I did not do each step. But can you try to find the expression? So this type of questions will give you some very standard results, which you should practice once, twice, and try to be very well versed about.
It's by sin hyperbolic beta h cross by 2.
Right. So you did it like this, right? Summation over n e to the power minus beta e n, and then it's something like this. So you get something like this. Is this what you got?
Yes, ma'am.
Right. So now this is your value of Z. How do you find the average energy? So you can do it in two ways. One is you can do a summation over. So what you can do is that means you have to do a summation over all values of En into e to the power minus beta h cut omega n plus half divided by Z. Okay. So you can do that. Or what you can do is you can do minus del beta of ln Z. We know that the average energy is given as minus del beta of ln Z. So you know the expression for Z. You can use that relation to find the average energy, right? So if you do that, you would get something like this, right? Is this clear?
Ma'am, I have a doubt.
Yes.
Find the density matrix from this. Is it?
Yeah, yeah. I just lost you. So you want to find the density matrix from here.
Yes, ma'am. In the energy representation.
Right. So in the energy representation, what would happen to the density matrix? So see, this is your Z, right? And how do you write the individual terms in the energy, like, okay, so maybe so maybe some state, okay, which is given as, let us take phi 1 and phi 2, okay? So we want that particular matrix element. So what will you do? We will do something like phi of 1, okay? And then here we have to have rho, which is given as e to the power minus beta h, right? Pi z. We know the expression for z, right? And then we will operate it on phi of 0. So what this will give you? This will give you something like rho 2 1 or something like this, right? Where the first state will be is represented by phi 0 and the second state is represented by phi 1, right? So this is your that element, right? So when you operate e to the power minus beta h on phi 0, what will you get? You will get the first eigenvalue which will come out, right? So you will get something like h cut omega by 2 that will come out by z, right?
Yes, ma'am.
Is that clear? And
Yes,
then
ma'am.
phi, then what happens is you have this inner product of phi 1, phi 0. Now what will that be? Inner product of phi 1, phi 0?
0.
0. So that means all non-diagonal terms will be 0. Correct? In the
Okay.
energy representation. Now what will be the diagonal term? Suppose now if we have to find rho 0. Okay, so this is 1, 1 maybe. So what will the value be then? So it will then be, we will take this the first value. So it would be e to the power minus beta h cut omega by 2, right? This is your first eigenvalue, which comes when you operate this operator on phi naught, right? and then you know the expression for z which you can substitute. So this comes out, right? And then you have the inner product of phi 0 with phi 0, which is 1. So that means this is your first element, the first diagonal element. So similarly, you will have all the other diagonal elements, and all non-diagonal elements will be 0. So that will be your density matrix representation. Is that clear?
Yes, ma'am.
Right.
Yeah.
Okay. Okay. Shit, shit, shit. Okay. So now the next question, next part of the question is that, so this is something which is always true, okay? Del x of trace of, do I have an eraser here? So del x of trace of e to the power a is equal to trace of del a del x into e to the power a for any operator. Now, given this relation, we have to show that the expectation value or the average of p square by 2m is equal to m omega square q square by 2m's average, right? And then from there, we have to find q square average. So how do we do that? So what we do is that, what is the expectation value of rho square by 2m? This is trace of p square, p square by 2m's expectation value will be given as trace of rho into p square by 2m, right? And similarly, expectation value of this term will be equal to trace of this term in this operator into rho. This is the definition of expectation value in terms of like using density matrix. Now we see that if you look at the expression for the partition function, what is the expression? The expression is this, and it has no m dependence. There is no dependence on the mass of the particle. Okay, so that means del z del m is equal to 0. So if you start with this expression for z, and if we differentiate with respect to m, this should be equal to 0. So that means del m of trace of e to the power minus beta h is equal to 0. And then if we use this relation that is given here, what we see is that we can take the trace out. So del m of minus beta h e to the power minus beta h is equal to 0. Now here, if we substitute the value or the expression for the Hamiltonian, what do we get? We get something like this, right? Here we have just substituted the expression for h. Okay, h is given as p square by 2m plus half m omega square q square. So this is what we have got. Now, what this again means, that means we are taking this on the right hand side. So we get this value, right? Now, what is the trace of h into rho? So h into rho, the trace of h into rho would give you the average energy, right? And that would be the average of this term plus the average of this term, right? Is this clear? So that means now if we say that trace of this term and trace of this terms are equal, this tells you from here you can see that that tells you the trace of rho square by 2m, and so e to the power minus beta h by z is actually rho, right? So this tells you that the expectation value of p square by 2m is equal to the expectation value of m omega square q square by 2. So both of these terms have same expectation value. So if we use this relation here, that means now if we have to find the expression for one particular term, both of these terms are equal, right? So you can write it as 2 into m omega square q square by 2, right? So individually, each of this will be half of the average energy expression that we have got. We have initially found the average energy expression, right? This is the average energy expression. So the individual terms is half of the total average energy expression, right? And now, because m omega square by 2 is a constant quantity, we can actually find the expectation value of q square, right? So this gives you the expectation value of q square. So similarly, you could have written the expectation value of p square by 2m as the same value, right? Both of them are equal. And similarly, you could have found the expectation value of p square. And here you can see that while like in the classical limit, you get something like this, okay? And then in the quantum result, you, okay, what have I written? While the classical result, okay. So what this tells you is that this is your classical result. So that classical result happens at high temperature, okay? And that vanishes when you go to t equal to 0. And at t equal to 0, what matters is the quantum result, which is given by this value, okay? And this matches with what you do out of quantum mechanics. If you just solve the expressions quantum mechanically, you'd see that this is the constant value of q square that you would get at 0 temperature. So that means again, at this proves at higher temperature you get back the classical result, at lower temperature you get the quantum limit. So is this thing clear? Do you guys have any doubt? Okay, I don't know.
No, ma'am.
Okay, so that means like, so using this kind of relations you can, so this is this the property that we use here is quite is a general property, and that would give you, so see, you could have very easily found this expectation value by actually doing those integrations, but that would be very tedious and very difficult, okay? But if you use these relations, it becomes quite easy to solve this kind of expectation values, okay? So that's it. uh, it- so if you guys have any doubt regarding whatever we had discussed today, you can ask, otherwise we'll call it a day. No doubts, right? Okay,
Ma'am, can we discuss a question from the previous assignment?
okay. What is the question?
Just a minute. Ma'am, can I share the screen?
Okay, 1 second, wait. Share, I guess. Okay, you can share.
I don't see the option.
Okay, I think it's some settings problem. So I guess you can share the question in the chat box maybe.
Okay, I will try, but the equation might not look correct. But I will try.
No, you can just click a picture of the thing and just upload. You can do that, or maybe I think because of the settings with I think it's because of the setting that is a problem. Okay, let's see. Consider the quantum harmonic oscillator with the Hamiltonian given by this. Okay. Formal expression for the canonical density matrix rho in terms of the eigenstates n and the energy level En is use your past knowledge of. Okay.
I could not solve that question, so
Yeah, but basically, what's the question? You have this quantum harmonic oscillator, your Hamiltonian is given, and then you have to find the canonical density matrix. Is it? So is it for a single, is it for a single oscillator? If it is for a single oscillator, then it's same as what we had just done. Like the canonical density matrix would be uh, 1 by 2 sine hyperbolic of h cut beta h cut omega by 2, something like that.
can you show how to solve this question because I could not solve it.
Okay, there were options. Is the answer that I'm saying there in the option?
This is old assignment, so the answer is shown now. Just a minute.
No, like options are, you would get the options, right? I'm not asking for the answer, but the options. I think this is for a single oscillator only, they have said. Single harmonic quantum harmonic oscillator with the Hamilton given by this, and these are the different energy levels. Okay, q prime rho q is equal to 2 sine. Okay, summation over n e to the power minus beta h cut omega in or q prime. Right. N plus 12.
No, actually, that's in the denominator. Hold on.
Uh,
The copy paste is messed up.
so basically, when the calculation that we were doing, so while you write, maybe I'll share again. Mm, so see this calculation that we just did. So this is how you write the uh, density. This is how you write the partition function in the energy representation, right? This is in the energy.
Mm,
Yeah, tell me.
can you enlarge the screen?
Yeah, I'm doing that. Oh, why is it not happening? Second. Yeah, okay. So what you do is actually see trace of e to the power minus beta h. Okay, so trace meaning summation over all values of so all the diagonal elements, right? So it's summation over all the energy level possible energy levels n e to the power minus beta h cut omega n plus half, because this is how your energy levels are defined, right? So basically it's summation over n e to the power minus beta en. Okay, so now if you break this, what you get is you get e to the power minus beta h cut omega plus no, so what you get for n equal to 0 is, so it should be, if you expand it, you will get something like e to the power minus beta h cut omega by 2 plus e to the power minus 3 by 2 h cut omega plus e to the power minus 5 by 2 h cut omega dot dot dot. Okay, it's a infinite series. So then if you take e to the power minus beta h cut omega by 2 common, what you get is 1 plus e to the power minus beta h cut by 2 plus e to the power minus beta h cut by 2 into 2 plus dot dot dot. Okay, so that's a geometric series. So what you then get is something like e to the power minus beta h cut omega by 2 in the numerator divided by 1 minus e to the power minus beta h cut omega by 2. Are you getting my point?
I think I'm understanding a little bit.
So basically what you are doing is you are writing, you are expanding this thing, okay? So you're expanding this. So what will you get if you expand? You'll get e to the power. So for n equal to 1, you'll get e to the power minus beta, okay, h cut omega by 2, right? And then it will be plus some term where you will have this 3 by 2, right? And then you'll have 5 by 2, something like this, dot, dot, dot. So then you take this term common, first term common. So what you will get is, you'll get 1 plus e to the power minus beta h cut omega by 2 plus this into 2, like that, right? So it's like, it's a geometric series. So infinite geometric series, it's given as a by, so the summation can be evaluated as a by 1 minus r, where a is the first element, right? And r is the term that you are multiplying. So if you do that, what you get is, in the numerator you get e to the power minus beta h cut omega by 2, right? And this is the same, this term is only being multiplied in the each term. So and then it would be 1 minus this term, e to the power, the same term, okay? So e to the power minus not 0. So e to the power minus beta h cut omega by 2, the same term goes here, right? So what you then do is, you divide this term, divide the numerator and the denominator by e to the power minus beta h cut omega by 2. So what will happen? In the numerator it will become 1, and in the denominator you'll get e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2, right? And that is actually 2 sine hyperbolic beta h cut omega by 2. So to the power minus 1 because it's in the denominator. Is this clear now?
Ah, yes, ma'am. Yes.
Right. So that is your z. That is the dense partition function when you are doing in the energy representation. Okay, but I think the thing that you shared was in the, so you have to find the individual elements in the, I guess, where is the chat gone? So that was in the position representation. So when you do it in, now when you have to do it, no, wait, so now when you have to do it in the position representation, what happens? Let me see your expression. So use the hint, you have to find the canonical density matrix. Okay, so now individual density matrix will be, so as I had as I just said in the uh, just few minutes back, so that is your z, what you found, right? So what are the individual terms? It would be e to the power minus beta in en, the individual eigenvalues, by z, right? And that will follow all the all the diagonal elements will be that, and all other terms would be 0. And that would be your density matrix in the canonical representation, in the energy representation, right? So that is what is given here. So if you look at the expression here, this is your z. So what is your rho? How do you find rho? You find rho like, so this is your z. Okay, second. Right. So this. So what is your rho n? So individual density matrix elements, all the diagonal elements will be given by this term here, right? So you will have a matrix where all the diagonal elements will be present and all other terms will be 0. And for each diagonal element, this is how your values will change. and this is the expression for Z. So that is your density matrix representation in the energy with respect to the energy eigenvalues. What is given in the question is that you have to write it in the position. So in the position representation. So in the position representation, you get something like this. So it's a very lengthy derivation. You can, I think, if you look at some standard books like Patria or mm, actually any standard book, they'll give you this exact entire definition derivations. It's very difficult to solve like line by line now. But see, if you now look at this expression here, this is for, so that means you can also have non-diagonal terms. And then when you put q equal to q prime, you would get the diagonal term. So I guess this is what they're asking, and that is being written in some, I don't know what form. So the process is this. So what we solved is in the energy representation, then you have to move to the position representation. That means you have to write the density matrix with respect to the position eigenvalues that is given by q or q prime. Okay. So each matrix elements will be this inner product. So I guess if you match with the solution, it should it should be this. But then I don't know if they're only looking for. I think there the question they are only asking for the diagonal elements. So there you can put q equal to q prime. This derivation, how you get to this is, I think if you look at the class videos also you'll get, or you can look at standard books like Patria or something. It's a involved process. You have to go through multiple steps.
Okay, ma'am.
Yeah. I think so. You can check with this expression. I think if it matches. I don't know what exactly the expression was. I just forgot. So, but in your whatever you had written in the chat box, that should match with this, I guess. Okay, so this is the general thing only they have written, I guess, right? So okay, so they have even not solved the entire thing. What they have written here is that okay, so this I think can be explained. So what they are doing is, so you want to find this, and you know rho in the energy space. So it's similar to this thing that we were doing, right? So when we did in the energy space, I get, see here, what did we do here? What we did is we knew in the position space, and then we went to the, we knew in the momentum space, and then we went to the position space. So how did we do that? This is what we want to find. So what you want to find is q prime for your question. It was q prime rho q. That's what you want to find, right? And you know what you know is maybe I can write it as E prime rho E, where E prime and E are the energy eigen vectors, right? So then you can write it in terms of the summation here. And when you expand rho, you will get that same. So here what you can write is you're writing rho in this representation that is already known to you, right? In the energy representation, we just found out. We know it's e to the power minus beta En by Z, right? So then that's why you have this sine hyperbolic term outside, because they have taken Z out, right? And then you have this summation. So what they have done is they have considered n vectors as the energy eigenvectors. Okay. So what is k or k prime here is actually n there. Okay. And then you will get a delta function. So ultimately you have only one k, and this k is actually n there. Okay. The energy eigenvectors, and what is r here is actually q for your case, for your question. Does that explain?
Yes, ma'am. I think I understood. Yeah.
So actually, because I can't write the thing, that's why, because it's it would be a elaborate expression, but I guess that's it. So see, e to the 2 sine hyperbolic beta h cut omega by 2. Uh, so 1 by z was in the denominator of rho, right? Rho was e to the power minus beta En by z. That's how you had defined rho n, right? So this 1 by z is written as 2 sine hyperbolic h, this term. And what you have inside is this. So here n are the energy eigenvalues, and q are the respective q prime and q are the respective position coordinates. Just follow this the how we move from the position representation to the momentum representation to the position representation for single particle, and use the same concept here. Here you will move from the energy representation to the position representation. That's the only difference.
Okay, ma'am.
Okay. Yeah.
Yes.
Okay. Okay. So if possible, I'll write, and maybe next day I can just start with this question, and we can see if you still have some doubts. Excuse me, still have some doubts. So I'll write, and then I think that would be that would make it more clear. But I think if you try to solve along this line, you'll get the answer. Okay.
Yes, ma'am. That would be better. Yes.
Yeah. Okay. 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 So thank you. I'll
Yes.
stop
Thank you.
sharing. Yeah. Welcome.